We are at 10:31, which is our usual starting time. And so welcome to the Joint Center for Extreme Photonics Friday seminar series. And so today we have Angela Gamoris from NRC and Jean-Michel Menard from University of Ottawa. And I forgot to ask who is going first. Okay, Jean-Michel, please share your screen.
David. Thank you, David. Yeah, so this week presenting this collaborative project between Angela and I, and we also have now a co-supervised postdoc, Gunchang Choi, who just started in March, which means that he actually stepped in the lab for the first time last week. But he's been working on theoretical work until then. So the title of the talk is Development of Sensitive Detection Techniques for Terahertz Radiation. And before starting, maybe a little bit about my background and also the setup here of this collaboration. So my group focuses on terahertz spectroscopy. We design photonics tools to get better spectroscopy capabilities in terms of sensitivity, speed, bandwidth, and we use them to extract new insights on condensed matter system. JCEP allowed me to team up with Angela at the NRC, where she works on metrology and single photon detection, and this is very different from terahertz technologies. But when we discussed, we realized we can combine these two experts together and access very exciting physics. And you may expect from this talk maybe to hear about terahertz single photon experiments. This is what we want to achieve. We are not quite there yet. It's a new field. It's technically very challenging. But so far we have some success already at improving the state of the art to get there. And we are also crunching some numbers to make sure we have the best approach. And in this presentation, we'll show you some of our recent success stories, some preliminary data, calculations, and also discuss our future plans. So more specifically, I will go first talking to you about terahertz applications and background and some recent advances in terahertz photonics in the lab on the grating-assisted non-collinear electro-optic sampling and also single pulse terahertz detection. And then Angela will take over and she will talk about her background on photon ecology and how we are aiming to implement terahertz single photon source and detection. So just to make sure we're all on the same page, when I talk about terahertz, I'm going to be referring to this region of the, I'm going to use the laser pointer here. This region here of the electromagnetic spectrum of light around optical frequencies of 10 to the 12 hertz or 1 terahertz. If you're more used to think about wavelength, this corresponds roughly to 300 micrometer of wavelength. People call it sometimes far infrared, mid-infrared region. We will call it today the terahertz region, and it's a loosely defined region. So even if I talk about 30 terahertz, I'm still talking about terahertz. So this is a fast growing field of research, but for a long time, this was a region which was very difficult to access. And this is here a diagram showing you the technologies, devices, and their output power as a function of frequency. And you can see here that are all these devices relying on electronics or the acceleration of free charges, and their efficiency drop as we get to the terahertz region. And on the other side, we have all the devices relying on atomic transitions or atomic-like transition. I think about the quantum cascade laser there. And again, the same story. So for this reason, this region of terahertz was often referred to as the terahertz gap. But this was 10 years ago or more. Now there's been some new techniques that people have started to develop, and this gap has filled up. And I'm going to talk to you more about these new techniques later in the presentation. So when I talk about terahertz, the first application that usually comes to people's mind is the security, because terahertz is a very nice radiation. It can pass through cloth, paper, ceramic, plastic, so it can be used to image through these materials. And for example, for security reason, it's very practical. So here in this recent demonstration, this person here is illuminated by different terahertz sources coming at different angles, and they take a picture of the reflected light, and you can see that, for example, if he has some dangerous objects, this looks like Coca-Cola cans, you can image them. If he has something that looks like a gun, you can also see it, but in terahertz picture, I don't know if you're like me, if you have some imagination, it doesn't look quite like a gun, it looks more like Kermit the Frog. And this just to say that there's a lot of improvement that can be made to get better imaging systems or even stronger terahertz sources. But you don't need a camera to image an object in actually any wavelength whatsoever. But in terahertz, this has been demonstrated recently, and there's many schemes. This is one of them, which is maybe the most recent one, where they use a large terahertz beam, they pass it through an object, and they reflected this terahertz onto a mirror, which changes shape. And this mirror is activated here by a blue light, which creates a density of electrons on which terahertz can reflect. And depending on the shape of this mirror here and the intensity recorded by a single pixel detector, the computer can reconstruct the object which was put in the beam initially. So all you need here is a fast and sensitive single pixel terahertz detector. Terahertz is also known for its spectroscopic applications. A lot of molecules will have signature resonance in this range. So if you have, again, good sensitive detection and you can do spectroscopy, then you're able to look at various compounds. This is also a recent study on the detection of viruses. Here they were able to not only detect viruses, but also differentiate different type of flu viruses. It's very impressive. Another large market involving terahertz is wireless communication. So right now the 5G system is a little bit below terahertz in terms of frequencies, but terahertz would also support 5G infrastructure and could also even allow faster data transfer in offices, for example. So that's a nice technology for this. Since the wavelength is a bit shorter than the current wireless communication bandwidth right now, this is more unidirectional. And also terahertz is also absorbed in air. So this would allow to have a confinement of the communication in 3 dimensions. So this is good for secure communications. And there's a lot of recent research on implementing terahertz for wireless communications. And some of them, I mentioned one of them here, which made it to Nature 2 years ago, was just about the possibility to put a scatter inside the terahertz beam and try to extract information. So eavesdropping on terahertz communication link. In my lab, we're mostly interested in using terahertz to look at phenomena in condensed matter. Previously, I've looked at the formation of Nexiton polariton condensate with time-resolved terahertz spectroscopy. One can also look at plasmons and inter-subunit transitions inside quantum wells, and in some cases, how they can merge together and form different types of polaritons. In my lab, we're also starting some projects involving vibrational strong coupling, so how a molecular resonance can be strongly coupled with terahertz light. And this is very interesting because lots of chemical reactions depend on these vibrational degrees of freedom. And if you can start to couple them strongly with light, then you can change these chemical reactions, and this is called polaritonic chemistry. So this is something we're starting to explore. And in the rest of this presentation, I will also talk to you about how terahertz can be used to access the properties of 2D materials and how we intend to use it to look at non-reproducible or chaotic chemical reactions. So before I told you that there's some new techniques that can be used to fill up the gap here. So let me now describe some of them. I'll start with these 4 techniques here. And then later I will talk about a 5th one. So these 4 techniques are as follow. One of them relies on the avalanche diode, where electrons can be accelerated very rapidly. And it's called the impact diode. This is the kind of technology which is used. I don't know if you remember when you used to go to the airport, you would go through some terahertz scanner from time to time. And this is the source that would be used for imaging, for terahertz imaging. So it's very powerful, but it's also limited in terms of frequency to the lower part of the spectrum, the low terahertz frequency, so 0.1, 0.2 terahertz, something like this. Another efficient terahertz source is the quantum cascade laser. So in this case, you have quantum wells, which are on which you applied a very strong bias. And so that, I don't know if you can see here, so that the ground state on one quantum well corresponds to the excited state of the other one. And this will be used as to invert the population as a gain medium inside a quantum cascade laser. And these inter-subunit transitions, they can be engineered to be in the terahertz range. Of course, one also can decide to go to a large facility like a free electron laser or a synchrotron to get access to a bright terahertz source. But this comes to its advantages and disadvantages, of course. And one of the technology which is one of the most I would say popular for commercial terahertz spectrometers is a photoconductive switch, where a strong electrical bias is applied between 2 electrodes here and can hold a lot of energy until a pulse, resonant pulse, will inject free electrons, and these electrons will be accelerated very rapidly, and this will emit a pulse. So this is a technology which is often used for commercial systems now. However, this is my personal opinion. I think there's some limitation in terms of how much energy you can get out of it, because you will always be limited to 2 dimensions, and there's all this interaction length that is not taken into account here for these geometry, at least. In the rest of the presentation, I will talk to you about this other one here, the one with the question mark, which is based on difference frequency generation, or a parametric process. And I will describe this one in more details, because during the rest of the presentation, I want to tell you how we were able to modify it and to improve it to look at different type of systems. So this technique starts with an ultra-fast near-infrared laser delivering femtosecond pulses, and these femtosecond pulses are focused onto a nonlinear crystal, which has a second-order nonlinearity and allows a difference frequency mixing process between 2 spectral components of this of the pulses delivered by the laser. So these are 2 spectral components here, and they interact nonlinearly to give rise to a low energy radiation, which is a terahertz radiation in this case. The detection of this pulse is based on a similar principle, where the terahertz and the near-infrared pulse are both focused onto another similar crystal, and the detection mechanism is usually understood as a Pockels effect, where this femtosecond pulse is really short compared to this long terahertz oscillation, and probe a local part of the terahertz field, which is effectively acting as a DC field here. And through a Pockels effect, this DC field will change the polarization of this near-infrared pulse. So we're going to get one data point. And then we repeat the process with different time delay between the femtosecond pulse and a terahertz pulse. And if we actually scan continuously the terahertz against the femtosecond pulse, we can retrieve the full oscillating electric field of the terahertz. We get phase and amplitude information, which we can also express in frequency domain by doing the Fourier transform. And this is a very powerful technique because if we put a sample in the terahertz beam here, we'll see that we have a time delay here due to the real part of the refractive index of the material. And we can also get some dips in the frequency spectrum coming out of this sample. And this is because we have some absorption. And so we can retrieve the complex dielectric function of the material from this measurement directly without having to do any interpolation. Now it's also a pulse technique, so this information is collected over a very short time. So this allows us to pump the sample and create a transient state and monitor the dynamic of the system, for example, after injecting free electrons inside the sample. So our group has been interested in trying to improve this the state of the art. So if we use, for example, a non-linear crystal, which is a gallium phosphide crystal, and we use a relatively thin crystal of 0.2 millimeter, this is the bandwidth that we detect coming out of this system. I will assume that we use a similar crystal here at the input as well. One can decide to change the detection crystal by a thicker one. Thicker one will give you more interaction length, but only more signal where you have phase matching conditions. So in this case, phase matching conditions occur around 1 to 2 terahertz, and you gain a lot in this region, but you also lose at the higher frequencies, which are actually very hard to access also with other technologies. So this is a zone which is very interesting for us. Now, what we have decided to do is to modify the phase matching conditions by imprinting a grating on the semiconductor that diffracts the near-infrared pulse. But the terahertz, having a longer wavelength, doesn't really see this modulation at the surface, so goes right through it. And this gives us a non-collinear geometry, where phase matching will depend on this angle that we create inside the material. And this allows us to tune the phase matching conditions, and by we have fabricated this here at U Ottawa, and this is the result we obtained by using this crystal in the detection scheme. As you can see, we actually gain a lot when we go around 3.54 terahertz. Now, since we can use it for detection, we can also use it for generation. It's a bit more tricky, but here the generation, we actually need a very efficient phase grading with that diffracts most of the energy into the +1 and -1 orders, and very little one in the 0th order here. And if we are able to, and when we do this, the contribution from both order can add constructively. And this is the same results I showed you before. And then when we implement this double grading geometry, we get the red line here in this graph, which shows that around 2 to 4 terahertz, we actually improve the terahertz amplitude by a factor of 20. And this is a lot. I mean, 20 may not be so much, but this is signal amplitude. So if we think about intensity, that would be a factor of 400 in enhancement. So that's, for us, this is a huge gain in terms of spectroscopic capabilities, especially at these higher frequencies, which are very hard to access. So far we have demonstrated the scheme with gallium phosphide. The gallium phosphide is very nice because it's not so expensive, and also you can go in the nano fab and do a lot of trials, and gallium phosphide is a bit like gallium arsenide, so there's some relatively well-established technique to fabricate structures on the sample. But if you look at the property of gallium phosphide and you compare the nonlinear properties to other crystals used for terahertz generation, such as zinc telluride and gallium selenide, you see that it is not the best nonlinear crystal. What is the best nonlinear crystal? Where the best nonlinear crystal would be a crystal which has a very high Chi2 coefficient. Obviously, because the generation and detection rely on this parameter. You would also want to have a material which has a high optical damage threshold. So even if there's some organic compounds that may have high Chi2, if they absorb the light or if they are sensitive to high power, it might not be the best material. You don't want to have a material which will absorb your terahertz. It seems obvious, but a lot of materials have phonons right in this region. So again, there's not so many materials left after that. And finally, maybe one of the most important factor that you have to consider is the phase matching conditions, which will determine the maximum thickness that you can use for your sample and the interaction length that you can use. So far, these are the parameters that people dealt with. So since more than 20 years, people have known about these, they've known for more than that, but they've tried to exploit these techniques for terahertz generation detection, and they dealt with these limitations. Now we come and we say there's this one, which is also possible. You can use a non-collinear scheme, and now this allows we can revisit all the different materials which can be used for terahertz generation and detection, and potentially find some that were discarded based on this phase matching conditions. Now they might become interesting candidates. So this is something we have been working with Angela and Koen-Chang recently. So what do we do with a broadband sensitive terahertz spectrometer? This is one example of application to it. We can use it to investigate 2D materials. For example, CVD graphene, which is scalable. It's a nice electrical properties. But graphene is very sensitive. If you put something on the surface, the properties will be changed. And it's also going to be very dependent on the substrate that you put it on. So we performed an experiment where we had part of the substrate covered with CVD graphene and the other part not covered at all. And then we performed terahertz transmission absorption measurements on these two spots. And we see in the time domain, there's not so much difference. In the frequency domain, it's a bit more visible. So this is just a Fourier transform of this transient here. And we see that there's actually some changes. If you divide one by the other, you get a transmission measurement here. And what we measure is actually the electric field, the complex electric field coming from these two spots. And the green coefficients here are parameters of the samples. So if we divide the two measurement and we obtain a transmission, we see that the transmission is really just a function of the parameters of the graphene here. And from this transmission, we can extract the we can extract the conductivity and the real part of the conductivity, from which we can fit it to a Drude model and extract other coefficients from the material, such as the mobility. And this is, I'm just going to focus on this one parameter here. And what we have found out is if you change the substrate on which you put the graphene, you'll detect different mobility of graphene, and we have been able to regroup them into 3 different types here. So dope silicon, so a sample which has some charge impurities, dielectric, which have maybe some trapped charges, and high resistivity substrates, which shows the higher mobility. So this is some of the information that one can get, for example, for terahertz spectroscopy, and these information will be, in this case, very useful for nanoelectronics involving graphene. Now I'm going to switch to a different experiment. We are also interested in studying non-reproducible phenomena. In standard terahertz time domain spectroscopy, the probe must always see the sample in the same state. So just to refresh your memory, this is a technique we use. We overlap a near-infrared pulse with terahertz transients, and then we get this data point here, and then we change the time delay between the terahertz and the near-infrared pulse, and then we can get all these data points here and reconstruct the terahertz, which, for example, may have passed through some material. Now, if this material changes all the time, this measurement doesn't make any sense. So we have to find a way to measure the terahertz in time domain for every single pulse instead of having a technique that relies on any averaging. So how do we do this? I'll tell you with a schematic here, starting from the standard terahertz time domain spectroscopy, and I'll show you how we can modify it to achieve the single pulse detection. So again, everything starts with a near-infrared ultra-fast laser. Part of the beam is used for terahertz generation. Part of the beam is used for electro-optic modulation of and detection by sending this pulse afterwards to a polarization-sensitive detection. The first step here is to broaden the gating pulse, the one which is used for electro-optic modulation, in the spectrum and in time as well. For this, we use all normal dispersion fiber, which allows us to broaden the spectrum of our initial beam to something which is very broad. And then we also stretch this pulse in time. This allows us to get a pulse which is a bit longer than terahertz pulse, onto which during this nonlinear process, the information of the terahertz can be imprinted on top of the frequency of this pulse. Now, to make sure that we have a lot of signal for this first experiment, we use a tilted pulse front terahertz generation in lithium niobate. This is a relatively complex way of generating terahertz, but it's also one of the most efficient to date. And so we have implemented this technique just to get enough signal here, and anyways. Then afterwards, you don't want to look at the polarization content of your pulse anymore. You want to have a spectrometer. You want to be able to detect these changes in the spectrum. But we wanted to see every pulse coming out of the laser. So again, we cannot rely on averaging techniques. So this is a bit tricky. So to be able to do this, we actually rely on fast electronics. And the way we do it is we take the pulse, we send it through a very long fiber where all the frequency information is the pulse is gonna stretch in time, but all frequency will occupy a different time. And then when we detect this pulse, we know that the time of detection corresponds to a different frequency. So we can retrieve the spectrum by detecting the pulse in the time domain. For this, we need a very fast photodiode, we need a very fast scope, and we have them, and I'll show you an example where it works. And we need also the capability to acquire the information at a very fast rate, so to follow the rep rate of the laser. Now, this is complex, but it's also a simplification. Actually, I'm just going to talk about the fact that the information that we imprint on this pulse is not the amplitude, but it's in the phase. So we need to interfere this pulse with another one to actually retrieve the phase information. So that's I would qualify this as a heroic experiment, but we've made some very fast progress on it. And I would say that individually everything works, and we have already started to put things together. So I'm very optimistic about being able to show you some results from this experiment next time we talk. This is just an example of dispersive Fourier transform, the spectrometer that I was talking to you about, dispersing all the frequencies in time and being able to retrieve them by using very fast electronics. This is the spectrum measured at the end of this fiber with a conventional spectrometer. And this is, by comparison, this is the time domain detection of these pulses at the output of a fiber. So you can see that it matches very well. And this is single pulse detection also. So I'll summarize here what I've talked about so far, and then Anja will continue the discussion. So I've showed you some recent successes on being able to implement a non-collinear geometry to modify phase matching conditions, and this opened up possibilities for using new materials for efficient electro-optic detection or generation. We have also used these technologies to do broadband spectroscopy in graphene, and we are and so right now there's students and postdocs working on single pulse terahertz detection, which we hope to be able to use soon to look at the dynamics of non-reproducible phenomena, some chaotic systems or chemical biological systems. And these are the some collaborators and also the group members that directly were involved in the experiments that I talked about. So Wei and Nicola work on terahertz photonics. Sam has worked on the graphene experiment. Rachel has worked for almost 2 years now on this single terahertz pulse detection scheme, and recently she was joined by Gonchang, who is also helping, and John Karsten is undergraduate students, which is actually helping us remotely on the calculations this summer. Okay, and now I will give the floor to Angela to give the second part of the talk.
Great, thank you. Can everyone see my screen okay? Yeah. Okay, perfect. Yes. Great, well, thanks so much, everyone, for staying with us this morning, and thank you, Jean-Michel, for getting us started off today. So yeah, so I'm going to continue with our talk about the work we're doing in JCEP. So the outline for this part of the talk, I'll be going on with what Jean-Michel was discussing earlier about how we're really combining complementary expertise in 2 areas where Jean-Michel, of course, has lots of terahertz expertise. And at NRC, I primarily work on radiometry metrology. So I'll give a bit of background about that. And I'll tell you how that is going to relate to our goals with our JCEP project. And I'll tell you about the JCEP project of our development of detection techniques in terahertz. And then I'll tell you about some of the applications we can use when our project really, when we get back in the lab in a more reliable way. So this is a very comprehensive figure, which shows a lot of different photodetectors from the spectral range of the infrared to the microwave region. This D star figure on the y-axis here is incorporating sort of the noise equivalent power of all of these types of different photodetectors you can see here. And as Jean-Michel started off with, through this spectral range, there's lots of different types of detectors, and in the terahertz, it's kind of interesting to see what's available and see what we can do. So I think a lot of us are familiar with silicon detectors up here, which their spectral responsivity really falls off after the 1 micron range. Next, in this area, there's a lot of semiconductor-based detectors. Some are more sensitive than others, and of course, as we advance here in our wavelength range, the sensitivity can degrade. This can be overcome by, by cooling some of these detectors, and in some cases to liquid helium temperatures. But as we advance on our wavelength scale here, there's also thermopile detectors, which are very broadband and especially flat. However, they're very slow and not very sensitive. And there's also other detectors that are very sensitive in this range. They can be based on superconducting materials, for example. And of course, they need to be cooled to liquid helium temperatures and usually require a lot of equipment and are very cumbersome to run. And these types of detectors have been shown to detect single terahertz photons, which is very impressive, and they have very sensitive techniques. And of course, a lot of the battle is even just distinguishing the terahertz photons that you want to measure out of all of the thermal photons that are everywhere. So this project is really focusing on this gap that you see here in the terahertz area, where we want to develop a detection scheme, sort of based on commercially available components that can give us some sensitive detection capability. So within NRC, I work in the Metrology Research Center, which acts as the Canadian National Metrology Institute, and specifically I work on optical radiation measurement. So thinking of that giant figure we just left from, we can measure optical power and spectral responsivity characteristics of photodetectors at the primary level from the UV to the near infrared. And we do this by using a device called a cryogenic radiometer. So this is a type of electrical substitution radiometer. And so this is useful because then we have these standards in Canada that then we can calibrate people's laser power meters, for example, and different types of photodetectors versus different responsivity and wavelength. So we do this with this device that has this black cavity here, and it has a germanium temperature sensor attached to it, as well as a heating component. So what we do is we open the shutter and we expose our black cavity to optical radiation. And this causes a temperature increase in our sensor, and we can measure that. Then we close our shutter and we use electrical power to apply heat to the sensor. And when we get to the same temperature difference that we've had with our optical radiation, we then know how much electrical power we needed to substitute the optical power. So this is how we get all of our optical power measurements in watts. And in this case, this is all traceable to the NRC realization of the watt. So we disseminate this calibration to these transfer standard detectors from this, this cavity, and this black cavity, even our electrical substitution radiometer, by using a very large apparatus. So at NRC, we use broadband light sources and a double subtractive monochromator, where we can select the wavelength of interest. We then have this optical path that illuminates the cavity inside our cryogenic radiometer. We have this very elaborate pin-and-pin system and custom apparatus that after we do our optical measurement with our cryogenic radiometer cavity, we actually physically move the whole apparatus and then align to our transfer standard detector. So we're measuring the optical signal on the transfer standard detector with the exact same beam as we are with the cryogenic radiometer. So in the last few years, we've been putting a lot of effort into extending these very traditional radiometry capabilities to single photon detectors. So single photon technologies are really becoming very popular and implemented in all kinds of places, including in medical devices, for example, of course in sensing applications, and of course in quantum information applications. There's really a lot of examples here where quantum or single photon technologies and detectors are being implemented. And so as Canada's NMI and NRC, we want to make sure that we have the capabilities to calibrate these types of technologies so we're not totally reliant on other nations for these types of things. So there's lots of different types of single photon detectors. There's PMTs, which are the oldest ones. There's single photon avalanche diodes, or SPAs, that are based on semiconducting materials. There's also detectors based on superconducting materials that are nanowire and based designs, and also transition edge sensors, which can actually resolve the number of photons. And there's different types down here as well. So depending on your application, you definitely want to pick the detector that's right for you. You want to consider the spectral range, which is, as we discussed earlier in the terahertz, very challenging. And there's also different characteristics you want to consider. And one thing that we've been working on at NRC is characterizing the detection efficiency of single photon detectors. And one thing to keep in mind as well is that the detection efficiency actually depends on your incident count rate, because the recovery time on these detectors is the dead time and the reset time. And depending on your fluence, how many photons you have coming in, the longer you're going to lose more photons, the higher your fluence is depending on this recovery time. So my colleague Jean-Wen Jin and I have been working on this type of calibration apparatus. So Jean-Juan has really done all of this lab work. He built this apparatus. And so I will describe it to you here. So there's a couple ways that some of you may have heard of how you can calibrate single photon detectors. There's also a photon correlation method that can be used where you need 2 detectors. However, this one, this substitution method ends up giving you similar uncertainties and is a lot easier to do. And you only need 1 detector. So this substitution method is really a double attenuation and substitution technique. So here's a photo of the apparatus in the lab. And so we start off with our calibrated photodetector that was calibrated on our cryogenic radiometer in our optical beam. We have 2 ND filters, and at first we'll have them both outside of the optical path, and we use our laser diode, and we measure the laser diode power with our calibrated photodetector. We then put in 1 ND filter, measure that signal again, take that filter out, put in the second ND filter, and measure the transmission of the second one. So here, since we have a calibrated photodetector, we're actually calibrating the transmission of these filters in situ in our apparatus. Then we install both filters and use our translation stage over here to put in our detector under test, our single photon detector. So this is how we transfer our calibration from our calibrated detector, which has been calibrated on the order of microwatts. And using these ND filters, we get down to the order of femtowatts through single photon detector. So this is what gives us our optical traceability chain up to our cryogenic radiometer. One thing that's very important with these types of detectors is the alignment. So the active area of these types of SPADs is about 250 microns. And so of course you want to make sure you're not overfilling the active area or you're going to lose out on your photons and your information. So in this particular apparatus, we have a 3D stage, and we actually go through a scanning technique and then align the active area of the detector centered on our laser spot size, which in this case is 17 microns. Another thing we like to do as a metrology institute is we like to compare measurements with other national labs. So here's an example of where we've compared some of our SPAD measurements with NIST in the United States with Thomas Garrett's when he was in Boulder. And so our apparatuses are quite different. Ours is all free space, where his is all fiber coupled except to the end. And so here we have some preliminary measurements on the different detection efficiencies, and they agree pretty well, considering the differences in these setups. So instead of using ND filters, Thomas is using variable fiber attenuators, and so that he can get to much lower power here. But these are very nice measurements that show the nice comparison with our US counterparts. So in metrology, of course, we like to have our SI traceability and love our SI units and like to compare measurements. But we also like to look at different measurement science problems, and that's really where we are here with this JCEP work is taking this metrology foundation and facing it to different measurement problems. And so now I'll tell you about our goals here. So in terahertz, as Jean-Michel pointed out and I mentioned earlier, there's some measurement and detection challenges. Usually these sensors are based on piezoelectric sensors. For instance, this one is a piezoelectric detector available commercially. It has to be chopped. It's very slow. There's also sensors based on micromachine antennas that are also available commercially, like shown here. And they have a tiny antenna chip installed here in the detector. And these types of detectors are really not that sensitive and generally have lower quantum efficiency and a really long acquisition time. So depending on what type of measurement you want to do, these really might not work out. But there's also really sensitive detectors, as we mentioned earlier. There's ones based on superconducting tunnel junctions, like this example here. So it's very sensitive and could image this IC card very nicely. However, this chip, of course, has to sit in a very large cryostat operating at 0.3 Kelvin and has this very nice apparatus, but that might not be accessible to everybody. Additionally, single terahertz photons have been measured using single electron transistors and a gated quantum dot. But again, not everyone has those things lying around in the lab. So the goal of this project is to really develop a new terahertz detection scheme, and a sensitive one based on commercially available off-the-shelf components, and hopefully develop something that will be scalable and relatively compact, hopefully. And as Jean-Michel mentioned, it's going to be based on electro-optic sampling. So we already went through that, so I won't go through that again. But also, we're going to implement some single photon detection in this area. So the scheme that we're proposing right now relies on difference frequency generation. And we have an optical probe, possibly in the visible linear range, and we're going to mix it with a terahertz photon. And then we have, of course, our difference frequency wave coming out, and then we'll have our wavelength filter in place in our scheme to get rid of our optical probe, and then we can detect our photons with a single photon detector. And yeah, our JCEP PDF, Gan-Cheng Choi, is working on the calculations for this. And so I'm excited to present some of the initial results here. And so the calculations he's been doing, he's made a phase matching code, and we've been detecting the efficiency of the difference frequency wave generation. And some of the initial parameters we've been using are listing here, where our initial intensity really gives us a peak pulse power of 1 watt per millimeter squared. And we're considering that we have a single photon in the terahertz area coming in per pulse. And we're considering a crystal length of 1 millimeter right now. So here's some example graphs from Gan-Cheng's code. And so, for instance, just in this example, we're considering a BBO crystal. And so we can look at the refractive indices in the terahertz as well, and also the different phase matching conditions and so on. So the laser that Jean-Michel has in his lab, the amplifier, is centered at 1030 nanometers. And so we've been thinking about the possibility of frequency doubling it and using that as the optical probe. So in this particular case, in this example, our omega-1 is at 550 nanometers. But then that gives us an output omega-3 of 560 nanometers, which some of you may know would be horrendously difficult to filter. So as these investigations continue, here's an example. This table summarizes some of the initial results that we have, and this is still ongoing. So we've considered BBO crystal and also silicon carbide and gallium selenide. And here, because of the difference in transmission characteristics, here with these ones down here, we've used the fundamental center wavelength of the laser in Jean-Michel's lab. So here you can see the different outputs, and also the nonlinear coefficient plays a big role here, as you can see from our efficiency equation. And so Gan-Cheng is now looking into different crystals, possibly in a gallium phosphide and so on and so forth, with different coefficients. We can see where else we can get. So another challenge here is the wavelength of the laser. And so, if you were going to specially filter 1095 from 1030 nanometers, then that would be, you could find a filter for that. But here, if we wanted to use, for example, a silicon single photon detector, this is going to be very challenging and likely impossible for this one, where the spectral responsivity and detection efficiency in that area is very small. It might be possible for the gallium selenide, but this work is ongoing, and so we're looking into finding the optimal material for this application. And so Gan-Cheng has also calculated the number of photons per second we would get out of these schemes. So after these calculations are done and we've picked our nonlinear crystal, where do we go from there? So there's different applications that we could use for this type of detection scheme. So with this improved sensitivity, we could actually improve the characterization of terahertz sources, for example, We could also look into different quantum electrodynamics phenomena and different, different spectroscopy techniques, like, thinking of different condensed matter systems. But one thing that's pretty exciting to think about is actually terahertz ghost imaging. So a lot of you have probably, I'm sure, have seen some version of this diagram. I picked this one because obviously I liked the ghost guy. And so we were thinking of how we could actually implement, in this case, we have the pump beam in our nonlinear crystal, and you get your signal and Euler photons going in different directions. And using your coincidence counting method, you can actually image your object here. You can image your object here with, you can image your object in this one path without, by having nothing in the second path. So we're really interested in seeing, what would happen if we had a terahertz NIR photon pair and this type of detection technique. So just a month ago or so now, Duncan England contacted Jean-Michel and I, and was very excited about the idea of generating terahertz single photons. And with this type of method, we could actually do a ghost imaging technique as well. And there's different techniques that have been presented, like in this paper in 2014, they actually presented a ghost imaging technique without detecting any Euler photons at all. So this would be a way, if we can generate signal and Euler photons in the NIR in terahertz, we could actually do terahertz quantum imaging without detecting the terahertz photons at all, which would be pretty cool. So in this type of scheme, there's 2 nonlinear crystals instead of 1. And the key here is that we're using the same pump laser. So the yellow here is the signal photons and the red is the Euler. And we detect the interference of the 2 signal beams with the 2 single photon detectors. And this interference changes if you put an object in the Euler path due to the coherence of the pump between these 2 crystals. So for more details, please see this paper. I don't really have the whole time we won't go into it right now, obviously, but this is a pretty neat technique. And if we could do this with terahertz photons without even having to detect them, that would be pretty exciting. This can also be extended to different types of spectroscopy. In this particular configuration, there's a linear configuration with 2 nonlinear crystals. And in this experiment, there's CO2 gas and a gas cell. And again, and in this application, they're using a visible spectral range and components for infrared spectroscopy. So they've measured these 2 interference patterns of the signal photons. And in this case, I think their measurements are all 810 nanometers. And so they can detect the different concentrations of gas looking at the different interference patterns here. So we've been talking a bit about how we can implement this in a terahertz regime, but it will likely be very challenging because, of course, of all the thermal photons that exist all around us all the time. So Guncheng has been working on using the code that he's built up for our difference frequency generation approach into spontaneous parametric fluorescence calculations, which is the classical version, sort of the classical version of calculations for the spontaneous parametric Dan conversion. So these are the geometries that have been considered here. This is very preliminary, and we're considering initial parameters here of having a 1 watt CW pump. And also we're looking into having either the signal or Euler being an optical or NIR frequency and the other being in a terahertz frequency. So these are sort of some preliminary graphs and results. And so here, this is considering a gallium selenide crystal, and the pump wavelength we're using, just for example, is 1030, like the fundamental beam of the laser presently, but we're looking into maybe getting a different laser for this, but we'll see. This is very preliminary right now. But then this would generate a 4.6 terahertz photon for this type of application. So the next steps here are to complete our efficiency calculations, both for the difference frequency generation for our single photon detection technique, and also for our spontaneous parametric fluorescence for the photon generation. And from these, we'll be able to determine the best nonlinear material for these applications. And then we'll select and order our components, and we'll get into the lab and get some measurements going. And thank you very much.
Okay, thanks, Angela and Jean-Michel. And those who would like to ask questions, please turn on your video and your microphone. Albert, I see, is the first one. Go ahead.
Thank you very much. I guess I have questions for each of you, but let me start with Angela, since it was the most recent one and is on my mind. It seems to me that there could be another single terahertz photon detection system, which something we used to work on is using Rydberg atoms. And so the idea is that you generate a Rydberg atom in a very specific quantum state, typically a high quantum number n, and then the terahertz radiation will be a resonant optical transition in the Rydberg manifold. The density of states goes like n cubed, so actually can be quite dense. And then the detection is also fairly simple and single particle counting, which would be based on applying a pulsed electric field to field ionize the states. And because of the highly nonlinear dependence of the field ionization rate on the Rydberg quantum number, if you absorb a terahertz photon, you can detect it, you can field ionize it with essentially 100% probability without detecting the initial state that did not absorb a terahertz photon. And I see that there's some recent papers. There's one I just found in, looks like in an IOP journal, where they compared single photon detection using Rydberg atoms with electro-optics and other methods, and they arguing that it has some advantages. So in the old days, for example, David Villeneuve and I used to work on detecting Rydberg atoms or Rydberg molecules with pulse field ionization. I wondered if that's something that is worth considering. It certainly can be the single particle counting limited. And so that was my question for Angela. My question to Jean-Michel is based on techniques people used in molecular alignment, where they also used these chirped pulses to detect the, using third order spectroscopy, using the optical Kerr effect, to look for the induced polarization rotation due to molecular alignment. It's also in the terahertz frequencies. But there they actually used a direct spectrometer that they would read out at the laser repetition rate, which is in the order of a kilohertz. So they, in other words, directly detecting the optical photons and through a cross polarizer. And the optical Kerr effect would only lead to the rotation of the color of light when the transient was there, and no polarization rotation when it's not there. So my two questions are to Jean-Michel: could you not, if you had a kilohertz camera, could you not directly detect the optical photons? And then about using single Rydberg atom detectors.
If I can answer first, yeah, if you have a spectrometer able to have a refresh rate on the order of kilohertz, then it means you can have a laser operating at a kilohertz rep rate and get your movie in the millisecond frame per, every millisecond you're gonna have a frame. So you can make a movie. We are right now operating at 10 kilohertz, which could work with this spectrometer, but we are just demonstrating a technology to be able to ramp it up to 100 megahertz, and where I'm not sure if you would get all the way there, but the electronic speeds for the scopes and the diodes would allow us to get there. So that's but I didn't know about the spectrometers that can get to 10 kilohertz or so. I'll look into it. Maybe that's can be very helpful just to help us to get where we want to be. I actually have never heard. You're you're telling me for the first time about this detection scheme involving a Rydberg atom. I'd like to hear more about that. I'll definitely gonna look at the reference that you mentioned. If you
Okay.
Yeah, it's definitely worth seeing what overlap there is. I mean, I guess like the goal we were going with here is to really kind of use really accessible, off-the-shelf components and things like this. But of course, you know, looking into different approaches is always useful.
Well, what's they argue, and this is how I thought of it, is that this is atomic physics is very well understood. So, you know, these atomic transitions, these cross sections are extremely well known. And so this could be sort of a traceability argument that although even if you don't want to, you know, make a field of, you know, a device you can disseminate based on Rydberg atoms, it could be an internal standard because the physics is very well known.
Mhm.
So I'd be happy to discuss further offline if you like.
Yeah.
Sounds good.
Okay, are there other questions from our studio audience? Duncan.
Yeah, so as you said, Angela, in your talk, I think one of the big challenges you're going to have with this project is trying to separate single photons that are very, very close to your pump. And we had a chat about this a while back, and since then I had a couple of things that came to my mind. And what I guess one that popped into my mind when Jean-Michel was talking. So have you thought about sort of non-collinear geometries for your detection scheme? So that would obviously physically separate the two.
Yeah, and Gunchang is looking into that as well. Yeah, and depending on the crystal and the phase matching angles and so on. Yeah, I mean, it's kind of interesting. Of course, Gunchang started, I think he got to the university the week before we all shut down. So, you know, the adjustment has been a little different than it would be normally, obviously, but things are progressing, which is great.
Yeah, and I was being distracted by my son building Duplo when you were talking about the gratings, Jean-Michel. But I wondered if there's the gratings on top of the non-linear crystal that you were talking about, if that would maybe be useful. But I must admit I didn't completely understand what was going on there.
The goal was to implement a non-collinear scheme, which can be easily implemented because you can always, you know, build a wedge, or you can always come with a really strange arrangement of pulses which overlap on the same spot but come from different angles externally. The grating is a way to get a very simple alignment of the two beams being collinear initially, and inside a crystal having a non-collinear geometry. That's very practical experimentally, and you just have to change the pitch of your grating to try different angles, and you can even build the grating with a chirp to be able to iterate over different phase matching conditions. So that's the main idea. Now, the one you were mentioning before, can you maybe even get a spatially separated photons generated because of this grating? And I thought it was interesting. This is maybe an advantage that we did not consider. Having already a grating there, maybe there's a way to separate these different frequencies, not only with a filter, but also in the spatial domain.
And then the other thing that I thought of as well was, could you use some like a type 2 crystal or whatever to try and get the pump and the difference frequency to come out a different polarization? Then you get a sort of, if you get a good polarizer, you get a factor of 10 to the 6 there for free.
Yes, they would. So this is basically the electro-optic sampling is based on that. It's based on the fact that you generate these photons with a different polarization.
Mm-hmm.
If you want to collect all of them, yeah, they might be. Yeah, I think you're right. Actually, I think a polarizer could actually enhance quite a signal there. Yeah.
Mm-hmm. Right. Cool. Thank you.
Okay. Anybody else with a question? I have a question for Angela regarding background radiation in the terahertz range. I have no idea what does this room look like in the terahertz range? Is it bright or is it dark?
Well, I guess it, you know, depends on the temperature of your room with all the black body radiation. So, but yeah, it's bright. There's terahertz photons everywhere. And this is, you know, I think this is going to be a bit of a challenge, but, and this is where I think with the detection technique where, you know, if we trigger it on the laser, for example, or something like this, we can filter out some of those room photons, but it's going to be a challenging measurement. I think there's no question about that.
Okay, can I say something more also, and maybe show a picture? So you're totally right. This is something we actually been thinking about, how to detect the photons that we generate and differentiate them from all the photons in the room, which is huge. This is here. Just allow me to share my screen for a second. How can I? Yeah, okay. So that's the thermal photons. They're everywhere around the nonlinear crystal that we use to detect and these are the photons that we want to detect here. And how do we differentiate them is by if we have a nonlinear process that basically we have a shutter, which is only the time duration of our pulse, and this can be as short as a few hundreds of femtoseconds. And so when you do this, you open your window over a very short amount of thermal photons. And right now we're polishing some of the calculations, but this is showing very promising that we would be able to, without having to cool down any crystals, anything in the room, being able to be sensitive to very few thermal photons while focusing on the one that we actually generate by single photon detection.
So this is gating your detector. Yeah.
Yeah.
Okay.
And the pulse also determines the area that we're probing, which can be very small. This requires a knowledge about the time of arrival of these entangled photons. But if we're also using a pulse for generation, then this is okay.
Yeah. So it's range gating in an imaging type experiment. Okay. Any other questions? It looks like it. So Peter and I are going out cycling now at different speeds. So next week we'll have our final seminar in this series, and then it will be summer vacation. So I thank everyone for attending, and I thank our two speakers for their presentations. Okay, goodbye.
Thank you.
Thanks, everyone.
Bye.